I think so.
Okay. So thank you very much, everyone, for coming today. It's like years. Should be I would have been so much richer and so much fun, and even the challenge together.
That was fun. That was fun. So, yes.
The student I was reading before I discovered the research areas and which there are many. So our research interests are in key numerical analysis with application, with computational. Ago, when you have this project with the modeling.
So I'm going to set up my very particular spin on eigenvalue problems. And I'm going to suggest one way of solving PDE eigenvalue problems. These are going to be by reduction to boundary integral equations or boundary integral eigenvalue problems. And I'll then try and walk you through 3 different examples. We'll see how far we get. I hope to get through the first 2. Certainly a lot of what I'm going to talk about today, the guts of what I do, is not just about spectral geometry, it's numerical analysis in general. And for some very nice techniques that would go further along this direction, you must come to Alex's talk. So Alex Barnett's going to be giving the other lectures in this series. All right, so what is spectral geometry? So according to Wikipedia, a few months ago, spectral geometry is a field in math which concerns the relationships between the geometric structures of manifolds and the spectra of canonically defined differential operators. Okay? And computational spectral geometry is the use of numerical techniques or computational techniques to study the interplay between the spectrum and the geometry of a domain. So why might you want to use numerical methods? Well, you might just want to get a picture, a heuristic, right? Something to add to your talk. You might want some reliable insights. So maybe you've got this PDE operator and the manifold is very weird. You don't know. Huh? That's Sakina. You don't know. Bonjour, Sakina. So maybe your hope is to generate some ideas for conjectures. Okay? And you could also think about using numerical strategies to help prove conjectures through validated numerics. I think the latter is a very interesting field. I'm not going to talk about it today, but there is an expert in the city on validated numerics at McGill, Jean-Philippe Lessard. All right, so in spectral geometry, when we're thinking about the spectra of these operators, there are three broad classes of problems. There are what I call direct problems, where I give you a domain, I give you the operator, and you compute the spectrum, or a finite part of the spectrum. There are the inverse problems, where I give you the spectrum, and you have to tell me something about the domain. And then there are the so-called optimization problems, where given the spectrum, I'm trying to find either the metric or the domain so that some function of the spectrum is optimized. Okay? And so canonical questions here could be like, can you hear the shape of a drum? So that would be an inverse problem. What's the drum that has the deepest tone for a fixed area? That would be an optimization problem. But no matter what you plan to do, you can't really avoid solving the direct problems if you're doing a numerical strategy. Okay, so the direct problems are what I'm going to focus on in this talk. Now we're going to think about, for a given domain and a given PDE operator with perhaps given boundary conditions, how do I find part of the spectrum? Which method you use will depend on both the goal and the questions of interest. Okay? So here are some prototypical eigenvalue problems. Let's think about, say, the Laplacian. I could ask for the Dirichlet eigenvalues, the Neumann eigenvalues, the mixed eigenvalues, where I have Dirichlet on part of the boundary and Neumann on other parts. I could have the Robin eigenvalue problems. I could think about the Steklov problem, where I have the spectral parameter on the boundary. So here the lambda, which is the eigenvalue, is on the boundary. I could insist that on part of the boundary, the Neumann derivative is 0. I could have similar problems for the elasticity operator, for electromagnetics, or for any other elliptic operators that you might want to work with. Okay? So just to give you a feel for what the eigenvalue problems, where you have the spectral parameter associated with the PDE operator in the domain. You could have electromagnetic waveguides or eigenmodes. So those are the figures on the left. You could have a waveguide with mixed data. Those are the L-shaped guys in the middle. You could have a resonator, which is this non-convex shape. Things can get pretty non-smooth. You could have a loss of differentiability. You could have sharp gradients. And these are all challenging things numerically. For the Steklov problem, where the spectral parameter is on the boundary, you have the famous sloshing problem, where you might have a fluid that's inviscid and incompressible. It's in a cup, like your coffee mug. None of you have coffee mugs, which worries me. Like, even the young people are not drinking coffee. It's only 4 o'clock. Anyways, so you have 0 Neumann data on the sides of the cup, and the surface of the cup is where you have the Steklov condition. Okay, so that's the prototypical Steklov type problem. So, all right, we've got these classes of eigenvalue problems. How are we going to solve them? Well, there's two broad classifications of methods. One is where I think about what's going on in the entirety of the domain. So those are the methods I call volumetric methods. Okay, and that's sort of depicted on the left. I try and enforce something at points in the interior. Okay. Or I could restrict my attention and my computational resources entirely to the boundary or to points very close to the boundary. Okay. So for example, if I would try to find the Dirichlet eigenvalues of the Laplacian, I would define something I call a residual, which is the mismatch between my approximate function times some guessed eigenvalue and the Laplacian applied to that guess. This is the residual, Rn. I could ask to minimize the residual over the entire domain in the sense of L2. And if I do this a little carefully, I'm led to a weak formulation for the eigenvalue problem. Okay. So this is a so-called volumetric approach. And there's a whole bunch of them. They're great. I love them. Here you see a finite element mesh. A finite element method is an approach in which you're discretizing the eigenvalue problem in the volumetric sense. And so here you can see the nodes, or maybe the edges even, are places where you enforce something about the residual. Okay? But then there's the class of so-called mesh-free methods, or what I like to call the boundary-based methods, where I'm going to pick a very special class of approximating functions. So I'm going to insist that my resources are dedicated only to the red points on the boundary. Okay. So how is this going to work? I'm going to approximate the unknown eigenfunction u through a finite dimensional vector space of trial functions Hn. These trial functions are going to be built in a very special way. They're going to be built so that each trial function satisfies the PDE, maybe with the wrong wave number, but they satisfy the PDE exactly in the domain. So I have no work to do in the domain. Okay? So the approximating function un is going to be a linear combination of these things. And then all I need to do is to find the coefficients and the wave number mu so that my residual is exactly equal to 0 on the boundary. And the residual now is exactly the boundary data. So if I'm solving the Dirichlet problem, I want the Dirichlet trace of un to be 0. The method of particular solutions consists of using trial functions that are particular solutions of the PDE operator. Okay, so for example, for the Laplacian, you would build your particular solutions out of Fourier-Bessel functions. And it's a very elegant, very nice way of solving eigenvalue problems in this boundary sense. Okay. There's another way of doing it, which is where you take your trial functions to be defined in terms of boundary integral operators. And that's basically what I talk about today. Okay. So here's a quick refresher about boundary integral operators. I'm not sure if all of you are familiar with this, so I thought I'd go through it a little bit. So suppose you have some elliptic operator A, or minus A, and you have a fundamental solution which you know. So in some distributional sense, the fundamental solution solves the problem in red. Okay. So you can use the fundamental solution to construct so-called boundary integral operators. You can construct something called a single layer, which is the convolution of a density phi against this fundamental solution. You can construct something called a double layer, where you take the normal derivative of this fundamental solution, you convolve it with the density phi. You could take the adjoint of the double layer, and so forth. Okay. Now, it turns out that if you took the single layer, so I give you a phi, you build S of phi. So this convolved object exactly satisfies the PDE inside the domain. Okay, so you don't have to enforce anything inside the domain. The only thing you have to worry about is on the boundary. Okay. Similarly, if you took the double layer or the adjoint of the double layer, it will also exactly satisfy the PDE in the interior. The only thing to worry about is what's happening on the boundary. So why would you choose one method over the other? Okay. So for the volumetric methods, it's very easy to deal with variable coefficients. I don't have to find a fundamental solution. I don't have to know a fundamental solution. There's the finite element methods, the finite difference methods, the spectral methods. If you have features in the interior, you can do like meshing, you can do adaptivity. This is all well known. And you're led to very large but very sparse matrices. So the linear algebra is easy. For the boundary-based methods, they work really nicely on constant coefficient problems, for which you have a fundamental solution. They resolve features on the boundary really well. And if you can compute the density that defines your single or double layer operator, then you can reconstruct things in the interior. You are led to small but dense matrices. Okay? So the linear algebra questions become very different. And they are serious. There's a lot of work that goes into trying to work with these small but dense matrices. And because the objects that we're working with involve convolutions of fundamental solutions or their derivatives, we need specialized quadratures. So here's a concrete example. For the Steklov problem, I'm trying to find a harmonic function u so that on the boundary, the normal derivative of u is a scalar multiple of the trace of u. Okay. So I can define the single and double layer operators as I did earlier as the convolution against the fundamental solution of the Laplacian. So the fundamental solution of the Laplacian in the plane is just 1 over 2 pi minus 1 over 2 pi logarithm of the distance between 2 points. Okay. So I'm going to use this as my idea. I'm going to be looking for the eigenfunction u as a single layer. So I shift the difficulty of my problem. Instead of looking for u, I'm going to say I know that u looks like the integral of my fundamental solution times an unknown phi. I'm going to look for phi instead. Phi only lives on the boundary. Instead of looking for something that lives everywhere in omega, I look for something that lives only on the boundary. Okay. Now this object is harmonic by construction. So I don't have to do anything for x's in the interior. Now, as I take points in the interior to the boundary, so as the point x in my integrand gets closer and closer to a point on the boundary, the integrand is going to pick up a singularity. And as a consequence, I'm going to pick up a jump in the double layer. Okay? So it turns out that the single layer is continuous, but the double layer will jump, and it will jump by a factor that depends on the solid angle of the boundary at that point. Okay? But if you take care of this, you're led to, let's see if I can do this. You're led to this equation in the middle. So 1/2 the identity plus the double layer operator acting on this density phi is a scalar multiple of the single layer. That's the new eigenvalue problem. Okay. So let's recap what I've done. I had a volumetric eigenvalue problem. I've converted it to an eigenvalue problem that only lives on the boundary now. Okay. The eigenfunction that I'm getting is not the one I wanted. Instead of getting u, I'm getting phi. But I can reconstruct phi just by remembering that u is the singular of phi. Okay, so I just have to integrate. All right. So just to get a feel for what's going on, if in the bottom I had some kind of a mesh on a square, what I compute is the density phi, which is in the middle. It just lives on the boundary. It doesn't look like anything. Phi looks weird. But that's not what you really want if you're studying the PDE eigenvalue problem. You reconstruct the trace by looking at the singular, and that's the top. Okay. Here's a different application, different way of doing this. So to solve the mixed problem for the Laplacian, where I have Dirichlet on some parts of the boundary, Neumann on other parts of the boundary, again, I could use a singular ansatz. Okay, so again, I'm looking for an unknown density phi so that the true eigenfunction is the singular of phi. And here, the fundamental solution I need to work with is a scalar multiple of the Hankel function. This is the fundamental solution of the Helmholtz equation. Once again, solving for the eigenpair in the volume becomes solving for the eigendensity and the eigenvalue on the boundary. So in this case, suppose I had some kind of boundary condition, say like I had Neumann on the blue pieces and Dirichlet equals 0 on the red pieces. I would enforce that the singular were 0 on the Dirichlet pieces, and I would enforce that the adjoint of the double layer plus the jump is 0 on the Neumann pieces. Okay, so I get a system of equations. That's what it ends up being. Once again, I have a residual. I need to set these quantities on the boundary to be 0. I enforce them through collocation. I'm led to an eigenvalue problem. So now the problem that I'm looking for is nonlinear. It's a bit of a mess because now the parameter that I'm looking for, mu, it shows up in the fundamental solution. So I'm looking for a mu and a density phi so that this integral operator is equal to 0 when it acts on phi. So now the plan is I'm going to look at this thing at a bunch of different values of mu, and then whenever I hit 0, I know I've got an eigenvalue. So the ingredients in these approaches are the same. You need to parameterize the boundary. You need to have a fundamental solution for the operator that you're working with. You need quadrature rules, and this is really important because the integrands might be singular or weakly singular. You need to get these integrals done approximately, but the quadratures are critical. And once you've put it all in, you're going to get a discrete problem. The discrete problems are either a generalized eigenvalue problem, AC equals mu times some other matrix BC, or you try to find the parameter mu so that A mu times the vector C is 0. So you're looking for the values of mu so that the matrix A becomes singular. You might need to regularize the problem. So it may be that the matrices that you get are kind of horrible. And I'll show you an example of where that happens. So let's take a slightly closer look at the Steklov problem because it's easier to start with this one. So for the Steklov problem, I'm looking for the unknown parameter sigma, which is a scalar, and the eigenfunction u, so that on the boundary, the Neumann trace is a scalar multiple of the Dirichlet trace. I'm going to not claim for a second that anything I'm doing is either brand new or hasn't been thought about before. So I'm just going to give you an example, highly incomplete list of references. So here's one page, here's another page. I could keep going. Okay. So please, I am not saying that this is the only way to solve the Steklov problem, and I'm not saying mine's the best way. That's not what I'm saying. I'm trying to show you there's a vast literature in numerical analysis on the Steklov problem. However, why is this such a fascinating problem for us? It's a very challenging problem. The Steklov problem is really challenging because, well, all the fun stuff is happening close to the boundary. So I've plotted here some eigenfunctions. This is the first, second, and I don't know, 6th or 10th, something like that. As the wave number increases, or as the spectral parameter increases, the eigenfunctions, at least in these examples, seem to concentrate near the boundary. So if you were doing something volumetric, you'll be trying to compute features that live very close to the boundary, and in the middle, they're exponentially small. That's really hard using a finite element. It's worse than that. So if you were interested in saying something about the eigenvalues of the Steklov eigenvalues of a domain, at least for smooth domains, there's this very nice result, and Alex is here in the room. The eigenvalues of smooth domains become nearly indistinguishable from those of a disk or sets of disks of the same perimeter. So if you were trying to do the inverse problem, okay, and I showed you that spectrum, you can't tell me which one of those belongs to the disk and which one belongs to the kite, a kite-shaped domain. And if you were using a bad method to compute eigenvalues, you really can't tell the difference. So you need very high accuracy, and that's one of the reasons why I think boundary-based methods are great here. All right. So I like to compute these eigenpairs using boundary integral approaches. I'm going to use a single layer. What kinds of densities will I use? What kinds of smoothness do I expect? Well, there's this nice result that tells you that the eigenfunctions, the Steklov eigenfunctions, are continuous up to the boundary. And so on smooth domains, I'm just going to pick my densities to be trigonometric polynomials around the boundary. Okay, so in some parametrization. Of course, in 2 dimensions, you need to be a little bit careful. So the single layer, it's Fredholm of index 0, but it's only injective provided the logarithmic capacity is not 1. Now, if you know what the log capacity is, great. If you don't know what the log capacity is, you really shouldn't care. Your numerical method needs to work even if you didn't know. Okay? So the fix for this is you add and subtract something clever. You add and subtract the average of the density, and you get something called the modified single layer operator, and you're led to an eigenvalue problem in red. Okay, this trick is pretty old. Once again, you solve this eigenvalue problem in red, you're going to get the spectral parameter sigma, you're going to get the density phi, and then you reconstruct it if you want. So what do the integrals look like? Well, if you can massage things by adding and subtracting the log of a sine squared. Okay, so you've got something that's singular, logarithmically singular. You add and subtract this very clever term. And so all the integrals that you have can be split into bits that are smooth and bits that are a smooth function times this very special logarithmic term. All the impacts of the parametrization of the boundary, all the other gross stuff that goes into M and M2. So the general form of integrals you need to compute on the plane, but here your integral is only around a curve parameterized from 0 to pi, it's of the form some smooth function times the log of sine squared t minus tau. So whenever you have a smooth integral, no singularity, just use the trapezoidal rule. You've got a function that's smooth and periodic, use the trapezoidal rule. For the guys that are logarithmically singular, there's a very well-known quadrature. The weights and nodes are written down. There's nothing to do here. Okay? So you put this all together, and your generalized eigenvalue problem gets turned into a discrete eigenvalue problem, and you just solve it. And the results are actually pretty spectacular. So on the disk, on the left, I'm showing you the sum of the maximum errors of the first 16 eigenvalues. And on the y-axis, you can see the scale is 10 to the minus 15. So we get all the digits we want. On the x-axis is the number of discretization points. So by the time you've got about 32 points on the boundary, your eigenvalues are correct to 15 digits. So that's incredible, right? I love this stuff. And on the right, you see the boundary traces of the eigenfunctions. It's not just the disk. If you had a kite-shaped domain, well, the kite you can parameterize on 0 to pi, or 0 to 2 pi. And if you take enough points, in this case, you have to take enough points to resolve the fact that you're going around a curve. Once again, by the time you have about 60 points on the boundary, you have all 14 digits in your eigenvalues for 16 eigenvalues. Okay? This is incredible accuracy. So our approach was used to answer a question in spectral geometry, which was, what are the domains that maximize the pth Steklov eigenvalue? So you just run our code and then do your optimization thing. Turns out they have p-fold symmetry. Turns out also that the maximizers are unique. And these eigenvalues have multiplicity. They have different multiplicity if p is even or odd.
Can I ask how differentiation is done?
For the shape optimization,
Yeah.
I don't remember. That was not, I didn't do that. That was Chowen and Braxton. Yeah.
If they're fitting into it, so you know, like the playing buttons. Yeah.
I don't know.
Or the critical base.
I don't know. I don't know. See, what I thought was cool was that some code we'd put out there into the world just got used by somebody. So that's all I care about.
So that's for a perimeter constraint, right? Not any.
No, this is perimeter constraint. This one was more recent. This one was also fun. So the question was, if you have Steklov eigenfunctions, well, they have parts where they're positive and where they're negative. So we call these the nodal domains. And it was conjectured for the longest time, or believed for the longest time, that the nodal sets are dense at order 1 over the spectral parameter. But then it turns out that that's actually not true. So I was at this workshop. It was a great deal of fun. Intuition is formed by the figure at the bottom right. We're thinking of a disk. The nodal sets oscillate like exponential I and theta. Okay. But if you perturb it just a little bit, then you get the figures, the other 3 figures, and the nodal domains there are not dense at the order of 1 over the wave number, right? You've got these big fatty bits in the middle. And that was a numerical observation that came about by using our code and then trying to be very careful about tracking where the nodal domains are. And then this was subsequently proved. We're able to actually tell apart the spectrum of the disk and the kite. So remember when I was showing you the Steklov spectrum, I can actually now tell apart the 2 things. I can tell apart how the difference changes as I vary the kite into the disk.
Did you say that it was they both have eigenvalues decaying like 1 over j?
1 over j to whatever power you want. They go very, very fast.
Oh,
Yeah, yeah, yeah.
curious to understand what the geometric, the parameter, the curvature, all of those things, how visible they are in the eigenvalues. But yeah,
So I did some calculations. I have some conjectures on it. I don't know what the state of the art is in terms of the correction. Alex?
Basically, it does not have an influence at any polynomial scale. That's
Yeah.
what the results say.
Okay.
It's infinitely fast.
okay.
But
But
of course, we
it's
don't put that
asymptotic.
constant in front. I mean, change the power, you change the constant.
Yeah.
So the eigenvalues die like exponentially.
I mean, they don't die, but the difference between disk and
Yeah.
this one is.
Yeah. So you can actually look at, if I drew a different kite that looked a little bit more kite-like, then it would also, the difference of its spectrum from that of the disk would also decay very sharply down, but it would kick in a few terms later. Yeah. So we've used these ideas to compute the Steklov spectrum on many kinds of domains, polygonal domains. Polygonal domains, you don't do what I told you to do. You do something different. I will explain that in a second. We can solve sloshing problems. We can solve the Steklov problem on multiply connected domains. And what's really nice, or what I value very much about the spectral geometry community, is that they come up with these clever asymptotic ideas. For example, on curvilinear polygons, it was shown that you can find these computable quasi-modes, and they depend only on the length of the edges and the angles between segments, and that these quasi-modes are very close to the Steklov eigenvalues. Now, if you gave me a weird shape, a weird polygon, you asked me to compute eigenvalues on it, well, I don't have the true eigenvalues, so I don't know how well I'm doing. But one thing I could do is I could compare to the quasi-modes. And this gives me a very nice sanity check to see what the quality of my approximations are. So here's an example where the top line shows you that using this approach I'm getting 6 digits of accuracy for triangle of a particular shape and 8 digits of accuracy for a rectangle. Now here's a twist. Instead of finding the Steklov eigenvalues of the Laplacian, I'm now going to find the Steklov eigenvalues of the Helmholtz operator. Why not? Okay, so here I fix the wave number mu. It's going to be real. And I look for functions u which satisfy the Helmholtz equation in the domain and whose Dirichlet trace is a scalar multiple of the Neumann trace. Now, suddenly, I have the possibility of negative eigenvalues. And you can see that by looking at the weak formulation of this problem. Okay? So if mu is large enough, I could have negative sigmas. I could also run into trouble because mu squared could be an interior Dirichlet or Neumann eigenvalue. In which case, if it's a Dirichlet eigenvalue, the term on the left in the weak formulation disappears. Yeah. So here's a concrete example. If I'm on a disk and the radius is r, then the eigenfunctions have the form Bessel function times e to the ik theta. And the eigenvalues are the ratios of derivatives of the Bessel function by the Bessel function at mu times r. Now, the enumeration here is weird. The k's and n's are not the same, but that's fine. The thing to worry about is what happens if the denominator vanishes. The denominator will vanish precisely when you hit a Dirichlet eigenvalue with mu squared. Okay? And what happens if mu is just a little bit before that? What happens if mu is just a little bit after that? So to show you what's going on the left, you see the second Laplace eigenmode on the disk. That's the thing we were talking about before. In the middle is the real part of the Steklov eigenfunction on the disk, same disk. This is for wave number 7.015. So I've taken parameters mu 7.015. I change it a little bit. I now go to mu equals 7.1, and you get the figure on the right. Okay. So for those of you that were at the talk, I think today, in the GEM mini course on analyticity with parameters, that's clearly not analytic. Right? So as I shift the wave number, my eigenmodes are not analytically jumping. That's not what's happening here. I jumped across a bad wave number. The eigenvalues are really large, or can be really large and negative. So the first and second eigenvalues could be like minus 12,000. Okay, but once again, I'm under, yeah.
Can I
Yes, sure.
check what's, if you track one of the eigenvalues is going through a pole.
Yep.
And it's flipping a sign
Yes,
through infinity.
Yep.
And that would look, the eigenfunction would look the same, right?
That's correct.
So, right,
that's correct.
the fact that it looks like a different one is because you just happen to be ordering them from the bottom.
That's correct.
Okay.
And that's the problem with the enumeration. That's why I said that the enumeration's all messed up.
Yeah.
But
And this is it's not a scaling.
yes,
So, yeah.
yes. And this is one of those situations where, okay, here it's pretty clear what's going on. And, you know there's a pole and you're going through the pole. I just discretized and I got some eigenvalues.
Right. Yeah.
And then I changed the wave number. I got some different eigenvalues. I just ordered them. And I went from minus 12,000 to minus 14. So what happened here, right? So to solve these problems, I also just use a single layer ansatz. You could do something else. You could use a double layer. You could use a combination of a single and double layer. I've used a single layer for these examples. It leads to a boundary integral eigenvalue problem, where again, I'm looking for the density phi and the parameter sigma so that the equation in the middle holds. For these problems, logarithmic capacity is not a concern. What is a concern is if the parameter mu is an exceptional value, or if mu squared is the interior Dirichlet eigenvalue. The discrete system that I get, well, I've got a matrix eigenvalue system. Mu is known, so I don't have to do anything fancy, but the matrix on the left could be 0 or singular. That's not so bad. The matrix on the right could be singular, right? So whenever you hit a Dirichlet eigenvalue, the matrix on the right is singular. And that's kind of bad, because if you don't know what the Dirichlet eigenvalues are, you're just trying to compute the Steklov-Helmholtz spectrum. You're marching along and you've got some wave number, and suddenly you've got errors that are on the scale of, it's hard to see. On the right, the errors can be like 10 to the 15, because the matrices are becoming close to singular and you're getting garbage. Yeah. So we need a method that's wave number robust. And so to think about this, we have to go to the Dirichlet to Neumann map. The Dirichlet to Neumann map takes Dirichlet data on the boundary, looks at the Helmholtz problem that's solved with that Dirichlet data, and then spits back the Neumann trace. Okay? And the problem for the Helmholtz equation is that at some values of the wave number, this operation is not well defined. The extension map that takes you from the Dirichlet data into a function that satisfies the Helmholtz equation, this is multi-valued. You have non-zero solutions to the eigenvalue problem, and so you can add any number of them. Okay? And so we have to change the domain of definition of the Dirichlet to Neumann map, or you can do so. What you do is, As long as you're not at an exceptional value, you just work with whatever space you had. But if you are at an exceptional value, you have to factor out the appropriate subspace. The details are not important as so much as the fact that you cannot have the same domain of definition for all wave numbers.
But you are saying before that you don't know in advance which are these special values.
Yeah.
So they still a problem now.
Yeah. But at least now I have a definition. And because I have this definition, this is a way for me to think about, aha, if my Dirichlet-Neumann map is only well defined in some smaller subdomain, I have to factor out some bad things. I must have to do the same at the discrete level.
So what you factor is like the Neumann data from the Dirichlet.
That's exactly correct. Yeah. So formally, that's what I would have to do. I factor out the space T, which is precisely the Neumann traces of the Dirichlet eigenvalues. But for those of us that are, like we do numerical linear algebra, say, I've got this generalized eigenvalue problem in the middle. Okay, it's got a matrix times a vector psi is sigma times another matrix times psi. What I'm going to do is I'm going to take the SVD of the matrix on the right, because that's the one that's the problem. So I take the SVD and I change the discrete eigenvalue problem. I just throw away any singular values that are smaller than a certain number. And I work on a subspace. So that's what happens. So this approach works really well. Once again, I have spectral accuracy for the eigenvalues. With this throwing away of the bad part of the null space of the kernel, I can get eigenvalues to very high accuracy. When you see a spike, it's because I'm reporting relative errors. So the spike occurs whenever an eigenvalue is super close to 0. So I'm dividing by 0. So on the panel on the left, my errors, my relative errors can jump up to 10 to the 20. That's because I didn't take care of the null space. If I take care of the null space, then my errors are 10 to the minus 15, except for the place where the denominator is close. I can compute eigenfunctions on a kite. This problem of the bad null space being an issue, it pollutes the entire spectrum for some problems. Okay, so the errors can be bad going pretty far out into the spectrum. So the curves in red are using the safe approach. There you get 15 digits. If you didn't, then your errors are bad, even as you go high into the spectrum. You can work on multiply connected domains. You can ask the question, what happens to these eigenfunctions as you go across the Dirichlet eigenvalue? You could set up like fun optimization questions. So this function here, if you double the domain, this function does not change. It has the right scaling. Turns out that if you plot the value of the objective function fk for k equals 1, 2, 3, 4, and 5, well, at first the curves seem to go up. Here, the x-axis is the eccentricity of ellipses. But then they start at a high value and they go down. So like there's this sharp transition. In each of these figures, the different colors correspond to the curves for different wave numbers. So the wave number so the curve in blue is capital F for mu equals 14. The curve in red is the same function, but evaluated for mu equals 15.3. So there's this nice bifurcation that happens as you've gone through a Dirichlet eigenvalue.
Sorry, explain what's the interpretation of FK? Like,
I don't know. We just came up with it.
what does it mean?
Okay, so
a I guess I don't understand sigma k of mu of
So-
omega.
right,
and
so-
what's mu of it, that's scaling of the Helmholtz parameter
That's correct.
to be sort of scaling there.
That's exactly correct. So when I double the domain,
Yeah.
the size of the interior Dirichlet eigenvalues changes.
Yeah.
So it's
Factor that out.
so I factor that out by changing the wave number. And then I want to keep the overall eigenvalue to be scale invariant. So then I have to multiply by, say, the perimeter. Yeah. This is not the only such quantity you could come up with. We've come up with some others. I don't know what physical interpretation to put to this. It was just some object we thought to play around with. All right.
It's this, but I should think of it as the scaled thickness of
Yeah.
S sigma of k.
That's correct. That's correct.
So there are many scales.
There are many possible scalings for this problem because you've now got this wave number in there as well, right? And the question of interest is amongst, let's see, amongst all possible smooth omega, which one optimizes F? Well, I don't care if I have a disk or double the disk, so that's why it's got to be scale invariant. And here I'm just looking over all ellipses, and this is what I got. Yeah. But there's a conjecture here somewhere. I got to state the conjecture more carefully, but there's a conjecture. I could work with polygons, and there are very, very sophisticated quadrature rules that are available because working with polygons, you cannot do the trapezoidal rule the way I described it. Okay. You can use polynomially graded meshes. You can use something called panel-based quadratures. You could do these exponential quadratures, and you could try different ones, see which ones are working. So in this particular problem, turned out for us, the graded mesh one worked well. We also tried an implementation that's available for MATLAB. It's called Chunky BIE, which I highly recommend. You could try that. We found that we didn't like tweak the parameters you could throw in there very much. The errors were marginally worse than ours, but yeah, whatever. What's really cool is that you can do difficult problems. You can find the Steklov-Helmholtz eigenvalues on L-shaped domains. And in the bottom two rows, you see the first few eigenvalues computed by other people. So the second to last row is computed using a finite element approach by Sun and Turner. The last is using a boundary integral approach, but a different one. And they did not factor out the kernel of the singular. And so they actually miss an eigenvalue. Okay. And you can see that we're able to get, using our polynomial quadratures, safely the spectrum very nicely, right? Okay, so how am I doing on time? I'm guessing I've got like -6 seconds. All right. So this next bit, I'm just going to race right through. You could solve the mixed eigenvalue problem for the Laplacian. Same idea. Pretend you're going to look for the eigenfunction psi or phi instead of u. Just do everything on the boundary. Okay, just use boundary integral operators. You're going to get, in this case, a pair of equations to satisfy on different parts of the domain. And then you have to take care of, we chose to take care of the singular behavior at the junctions. We did something called Fourier continuation. So on smooth domains, the eigenfunctions have singularities that look like the distance to the junction to any power n over 2. Okay. So we use something called Fourier continuation. We decompose our integrals. We do FFTs, and then we end up with very, very accurate methods. We have issues with conditioning. This is identical to the issues that arise, or the manifestation is the same as that happens for the method of particular solutions. The cause here is a particular problem with the Riemann-Lebesgue lemma. We fix it the same way that the MPS is fixed. It works like a charm. We can compute eigenvalues to high precision with very, very few points on the boundary. So in this example, if you're using a finite element method, you need, let's say, P2 on 5,000 triangles. You get 4 digits. We use 512 boundary points, and we get 14 digits. That's what they look like. And then you could do optimization with this. You could improve the gain in a room. Like we had this problem with meta-tunable resonators that change boundary conditions from Dirichlet to Neumann. Some cell phone company gave us some money, something. Doesn't matter. Doesn't matter. Point is, we use boundary integral operators here. It's a very flexible approach. You don't have to use polynomials. You don't have to do exactly what I told you. You could use a combination of single and double layers. You could use rational approximation, but it allows you to solve problems where maybe your domain is exterior to a curve, or maybe your curve isn't even closed. So you've got poles or resonances. Any of this is possible if you're willing to work on the boundary. So you can do this for any elliptic problem as long as your coefficients are constant. And so really the take-home message is if you can throw all your hard work onto the boundary, it might be worth it. That's it for today. Thank you.
Well, thank you very much, Nilima, for this inspiring talk. Are there any questions? We had a few just now.
So, there are interesting conjectures about eigenfunctions, eigenvectors of energy, which may be difficult to prove for a single metric, but it may somehow be true if the metric is random enough.
Oh.
Can you try and prove any kind of randomness to decide what kind into any interesting just to see numerically if this has any chance of being true, because
so with a random metric, my PDE operator, right?
Potential.
So okay, so there's a shallow answer, there's a deep answer. The shallow answer is I could probably throw noise into any part of the system and see what I get, but that's shallow. I'm not doing anything principled. If the coefficients of the PDE are changing or are random, then I'm in trouble because this method is using the fundamental solution with constant coefficients. So I should not be changing that. I could think about random perturbations of the boundary. So I could look at what happens there. I could try putting a spectral measure that's random, but that might change the quadratures I have to do. So that's not a regime I've thought about at all. But it's a good question.
Yeah, could also do perturbation theory with respect to the random metric. Yep. About the flat metric, right? So you would, if you just could get a volume source. Yep. That would, like a Helmholtz volume source would tell you at least as you start to randomize the metric how fast the eigenvalue is going to move.
You could follow, yeah, you could try following the eigenvalues through a flow of some kind, like a spectral flow type of thing, yeah.
Now, how do these methods apply and perform in the case of embedded surfaces in RTP, like say compact Riemann surfaces or genus?
Okay, so okay, I'll give you the shallow answer and I'll give you the honest answer. So the shallow answer is if you've got an embedded surface and you can parametrize it, you can do this. Okay, so there's no problem writing it down. The difficulty might be finding code, right? So
but you wouldn't know the fundamental solution specifically, right?
That's why the answer is shallow.
Oh, okay.
Right? So the ingredients are the ones I described. You parameterize your surface, you have a fundamental solution, you have quadrature rules, and then you can proceed. But there's a lot of ifs and buts in here, right? So if, for example, you were thinking about the Laplace-Beltrami, then indeed there's work by Mike O'Neill and his student in 3 dimensions. So they've worked on the boundary value problems for Laplace-Beltrami, and they've done it through a boundary integral approach. So they have the code, and you can adapt it to eigenvalues. But if you have a general metric and a general manifold, you have to write the formulation down first. So
Sure, I'll ask about the Fourier continuation. So that was a way to get around having to do singular quadratures, is that, do I understand it?
So what
An alternative to graded refinement?
That's correct.
You know, you have you said half order powers.
That's correct. That's exactly correct.
Then, so how does it get around that, if you like?
I'll show you. So I think this is an example
you know, you recommend it more than just direct discretization.
for this particular problem, because we knew the singular behavior had exactly this feature, it worked like a charm. So let's think about the arc cosine on -1 to 1. Okay, so this has exactly the same sort of singular behavior at the endpoints. So if you did a cosine change of variables from -1 to 1 and you took it to 0 to pi, you might pick up a Gibbs phenomenon at the end. So what you want to do is think about extending your function somehow smoothly to 0 to 2 pi. This comes at the cost of picking up not just the cosines, but also the sines. So if you're doing a Chebyshev expansion, you only see the cosines, but now you see the sines as well. And you have to have them because things are singular. But okay, you're working now on 0 to 2 pi. You can do your FFTs. And then when you reconstruct, you only stare at what's happening 0 to pi.
In parabolic space, there is this Helderson transform, which sort of, instead of looking at some functions of the disk, you look at some their boundary values on the certain infinity. So it's kind of adapted to hyperbolic metric. So I guess because people try. I suppose some people may have tried. Certainly, like Strohmeyer and company.
I was going to say Alex Strohmeyer is the only one I know that does numerics and hyperbolic geometries. Yeah, I don't know. I don't know. Yeah, I don't know.
I have a very nice question. Is there a way you could do a volumetric approach and then in the discrete world do a binary operator, discrete binary operator? And if so, would that commute with going directly to?
Ooh, yeah, so okay, so if I understand correctly, what you're asking for is like a sure decomposition, basically. So you've got if you discretize in the volume, you're going to get a large matrix, and some blocks are going to correspond to the boundary, and then the rest are going to be corresponding to the volume. And so you're trying to see if you can just focus on solving the problem on the boundary. That's a sure decomposition. I think, yeah, I think that is going to be tantamount to that. Yeah, yeah.
Thank you all for the coming. Don't forget there will also be lectures tomorrow, Wednesday, and Friday. Do you have anything?
No, I just invite you to follow up the next lectures.